So for the next section, one second. Okay. So we already covered Python. Now I'm going to talk about other language environments. There are many, so we cannot cover all of them. We usually see people using mostly Python, R, and Julia in our clusters. There's also quite some Perl, but that's getting kind of old, and a bit of Java, which is also becoming old. So we picked the R and Julia languages, just to have an idea how many here in the room are using R in their, okay, and Julia? One, okay. So for R, we already provide R as a module, so you can easily use it in our clusters by just loading the R module. And it comes with two bundles. One is called the CRAN bundle, and the other one is the bioconductor bundle. And those contain a lot of R packages from these repositories, from the CRAN repository and the bioconductor repository. With these two combined, you can easily load 1,000 R packages in our clusters and use them right away without bothering about having to do your own installations. And you might also find some other modules that are actually R packages, but they're separate from the bundles. And usually this happens if those R packages have additional dependencies. Like, for instance, they not just depend on the R environment, but they have another library or program that needs to be loaded with it. So, like, for instance, the R PostgreSQL, it needs a PostgreSQL database to work. So that's why it's a separate module. So you can find all those packages there. To look for R packages, since I said that they are in bundles, so it's to find them by name, you can do that with the spider option, well, the spider subcommand of the module command. And that's because the thousands of packages that are in the bundles are listed as extensions of those modules. So you can just, like, for instance, try to find the ggplot2 R package, which is a common one. And then the module command will tell you which versions are available as extensions. And then by executing again a spider with that specific version of the extension, it will tell you what module you need to load. So for instance, here at the bottom of the screen, you see that to load ggplot2 version 3.5.1, I have to load the R bundle CRAN module version 2.24.11, blah, blah, blah. So that's your way to actually find the packages that you need with the modules that already exist in the cluster. However, you can also install your own R packages, and that might be necessary. However, the difference or the particularity with R is that there's no really a package manager in R. Like we have pip for Python, or for instance, all the capabilities that come with Conda. In R, that does not exist, at least by default. There are external tools that we can use, but the support, the bare bones support is very limited. So there's the install command that you can use, and you can just do install packages, ggplot, and then it will try to install it. It will just download it from CRAN. It will install the last version. You can even specify with the install version function specific version to download. And that comes from the remotes library. So it's already not base R. You need to load some libraries. And then there are other functions like install GitHub that will install the package, but instead from downloading from CRAN, it will come from any GitHub repository of your choice, which might also be handy to use if you want to install some code that comes from that is in development, or it has not been published in CRAN. That can happen. And you can also install packages from your from a local file. Like you can download the source code of your package as a tarball or a zip file, and you can install that with the command install packages as shown at the bottom of the slide. And all that works, but the outcome is a bit unreliable. And that's because R will install those packages by default in what it's called your user library. and that just sits in your home directory, and it is tied to the R version that you are actively using. So because you are executing these functions inside the R shell, so you are already picked some R version, probably from a module file, and it will create a subfolder in your home directory, and it will be tied to this version. So whatever you install, it only exists for this version of R, but it exists for all versions, for any time that you use this version of R. So you have little control over when you want to use some package or when not. R will just go to this folder whenever this version is used and grab anything that is in there. And by using the function libpaths from R, you can actually see what are the sources of packages that R will check to load any libraries that you request. The first one is always the one in your home directory, and then you might see others that come from the modules that you have loaded. And then the last one is always the library of R itself, which in the case of modules, if you load R from our modules, that's a read-only directory. So it's not possible for you to install more stuff on the library that comes with R, only on your user directory, or if you define any extra directory. So by default, the installing packages with R has some downsides. As I mentioned, it's very hard to get some reproducibility out of it because you don't have a file where you can specify all the versions that you have and then just install those in a reproducible way. R by default will just take the last version all the time. There's also no isolation because, as I said, the library of R packages is just tied to the version of R that is active. So whenever you have used that same version of R, your user library will get loaded, and libraries from there might be loaded. And you cannot just activate or deactivate those arbitrarily. And it's also not easy to port those installations to any other system because it's also not that uncommon that an R package is just not pure code in R, but it might do compilations. So it might have low-level code in C, for instance, and it might just use the C compiler to generate some binary. And by default, that is tied to the architecture of the system you're using to build and install the package. So it will break if you move to a different system, a different compute node, or a different cluster that has a different hardware architecture. So to solve all these problems, there's a better solution in R, and those are RStudio projects, which is something developed by RStudio. I guess that the ones, well, for those that do not use R, RStudio is an IDE for R, like a graphical interface for R, where you can just easily develop code in R and execute code in R in a nice graphical interface. And they have a nice solution called RStudio projects, which is very similar to the virtual environments we talked about for Python. So in the VSC, we develop a new tool called VSC R project. And that was developed by K11. And this is a little tool that we have installed in all our clusters, and that serves to kind of use all the power of RStudio projects, but without needing to run RStudio. So it works from the command line. You can use it in your own scripts, in your jobs. You don't need to actually go into RStudio itself to use it. And then it's very nice because it works very similarly to a virtual environment in Python. So you can just define the modules that you want to load, like bundles of R, any other packages that you need to use in your job scripts. Then it will create an environment that is well-defined. And then from there, you can install any R packages that you additionally need to the ones that are already provided by the modules, and then use those. And that you can move around, and you can reproduce it very easily because it's all well-defined in a file. And now I'm going to showcase this for you. By the way, so that I'm going to run this demo, all the output of the demo is already in the slides. So you can follow on the screen or on the slides as you wish. It's more or less all the same. So this is my VSC account in my cluster. So the first thing I'm going to do is remove what I did. So the first thing is to actually load the VSC R project. I'm going to type. Oh my God. Typing is hard. So, okay, the VSC project module is loaded. And now what we need to also do is similar to also the VSC VM tool. We need to create a modules file, which I already have it here, which is, you can name it whatever you like. But here, for instance, I have a module file. Is this big enough? I have a module file that it's called my R project modules.txt, can be called whatever. And then inside I load version 442 of R, and also the bundle of bioconductor. So this will already provide a base with the thousands of packages that are already installed in the cluster. And then on top of it, I can, in my environment, I can install any extra stuff. Then to execute the VSC R project, I'm gonna just look at the script to not mess things around. And the command is this one. So this will by default create a project called my project. By default, it will be located in your VSC data. And it will use whatever modules are defined in this file that I'm giving as an argument in the modules -modules option. So as you can see in the output, it reads the file, it starts to load all the modules. And then it creates the folder with the name of the project inside the R projects folder in your VSC data. So whenever you create a new project, it will be just another folder in that R projects folder. And then in that folder, it creates a bunch of files that are the files that usually define this, the environment of these R projects. Once this is done, you can just activate the project. So this is just the creation. It does not activate it. And to activate it, you just need to actually run VSCR project with the activate subcommand and the name of your project. And it will look for that folder in your VSC data. Load the modules, prepare the environment. And now it will tell you how you can just run any script that you have in that environment. That's just as easy as just changing the directory to that project folder. So you can just cd into that folder, which is conveniently put into an environment variable in this session, which that is done by VSCR project. So that's automatically done. And then this is the contents of the project. And if I check the modules that are loaded, you can see that I got all the modules and all the dependencies to get up to the point where R bundle bioconductor is loaded. And now here, I can actually just run the R shell. And now this is maybe too big. And here you can see, so you get the usual message of whenever the R shell is started. So you get here the version of R, which corresponds to the module that we loaded. And then you get some extra information about the project that you are in. So it tells you the name of the project, where it is located, and you can see the library paths. Now the top library path is not the one in your user directory, but is the one in this project. So whenever you install something, it will go into the project, and you don't have to worry about what happens with the library in your home directory. You don't have to worry about filling up your home directory and all that stuff. So what I'm gonna do now is I'm going to execute an installation, but well, this will generate a lot of stuff. So I'll probably switch in the meantime to the slides, because the output oops, the output is very long, so there's no point in looking into that into the terminal. So I'm going to install a little package called VGDB. This is not TVLite. TVLite does not exist in R, so there's no analog to that in R. So I just picked some package from bioconductor, random package. So it's just some package to access some database of bioinformation. So it will start to install. Now it's doing all the resolution of dependencies. And it takes a while because there are thousands of packages now in the stack. But we can look at what happens in the slides because I already selected the important bits of the output. So first, it will tell you exactly what this bio manager, which is, by the way, this is the package manager of bioconductor. What the package manager of bioconductor is going to do, it detects the version of bioconductor that is already active. That's the one that comes from the module. And then it will analyze everything that is already available in the module and then install what is necessary for your package to actually work. And in this case, it determines that it needs reticulate, top-go, and data, and red, and also the BGDB that we requested. And it will download and install the following versions of these packages, which I listed here on the side. And then at some point, you will see that it does actually compile some stuff. And in this case, in the middle of the output, you will see that to actually install reticulate, it needs to compile low-level C code. And it will tell you that it is using GCC version 13.3. And that's actually good because that's the GCC compiler that comes with the toolchain of modules from the version of R that you are using. So it's actually using the same version of GCC that was used to actually compile R and install R. So it's all consistent. It does not use the one from a very old one, for instance, or some other external version. And another important bit is what is highlighted here is this March x86-64b4, which might be obscure syntax, but this option to the compiler tells the compiler to compile code that can actually work in a very wide variety of hardware architectures. So in this case, the v4 set of flags of 8x86 actually covers all the clusters in the VSC network. So any code generated by this option will work in all our clusters. And that's also very useful because that allows you to actually use this R project very easily between the different clusters or with your colleagues. You don't need to actually reinstall everything for every different cluster. And then at some point, at the very end of the output, once the compilation is done, all the dependencies are installed, R will tell you, OK, BGDB is installed and you can use it. And you can just load BGDB and use it right away. And in here, it's still not done. It's now installing and data. I'm not going to wait for this. But yeah, you'll have to trust me. We're not going to wait for this to finish. It's a bit long. And then you can use it. And that's how you can actually get like virtual environments, but with R in our with the VSC R project tool. Now for Julia, things are better and worse. It depends on how you look at it. So Julia has a very powerful package manager, and it has a very powerful environment tooling. From the let-go, Julia came with its own package manager, and it has a very well definitions of your environment. So you can define environments in Julia that where all the versions of all the packages are hashed. So you know the exact hash of the software that you're using, and you can reproduce that to the bit in any other cluster. But that also makes things more complex to work with, because if you have a colleague of yours or you find some it's called a Julia project or a Julia project environment. If you have if you find a definition file on the internet and you want to recreate that, and then you want to modify it and add your own stuff on top of it, that's not that easy sometimes. So it's it could get complicated. This also makes it complicated to actually for us to install things with Julia as modules, because Julia expects that everything belongs to a project and to an environment. So having just a module load and provide some libraries, but some other libraries from your own project environment, Julia is not designed to work like that. Everything is in the environment and the project, and things outside are not loadable by default. So you will see that in many clusters, you will only find the module for Julia and nothing else. And that just provides the basic Julia interpreter, the Julia command tool, and nothing else. We can have some modules of some extra, of some software packages on top of Julia, and we do have a few of those. The most common one is iJulia, which is the kernel that is needed for notebooks to actually execute code in Julia. But again, if you want to create your projects, it's very easy. It works. All the tooling is in Julia inherently. But you will have to install everything on your own. So basically, you will load a module of Julia, which I can probably show that here. Oh, look, BGDB was installed. And you can see here, done BGDB. And then it tells you, well, that a bunch of stuff was replaced by the installation, but that's fine, that's expected. So I'm going to quit this. Oh, and I forgot to mention, you can just deactivate your environment as usual with the deactivate command. And then I probably don't need to do this. Well, I'm going to remove the VSCR project. So for Julia, things are easier. So you can just load a module of Julia, the one that you like. We have usually, it's not difficult to provide multiple versions of Julia. And what I will probably do, well, I'm going to remove what was already done. And yeah, I can actually just go there. So I made, that's arbitrary. So I made a directory in VSC data called Julia projects. And then making a new environment is basically making a new folder, which in this case, I'm going to call again my project. And then you can just run Julia. And you get into the Julia shell, similar to the R shell or the Python shell. And then in Julia, the package manager is just called package. So this loads package. And then you can do package activate my project. I'm mistaken. OK, and it activates the project. And that's it. So that's the simplest way of getting an active project in Julia. This will generate in this folder two new files, a manifest TOML file and a project TOML file, something like that. And those files will actually keep a record of everything that you install in this environment, in this project environment. It will keep, as I said before, the hashes of the versions, the URLs, the locations of the repositories where the source code was downloaded. Mostly everything is downloaded from GitHub, and that happens automatically. So without you needing to define any of those repositories. And then to install something is just the package add command. And in this case, we're going to install a thing called tight binding toolkit, which I picked because it's similar to TVLite. It's a time binding model. And then Julia will start resolving package versions as usual, and then deciding what is needed for this to run on your system and installing a bunch of stuff. Now, very important with Julia is that it's very good that the environments are self-contained. So as I said, it's actually very difficult for us to provide modules for Julia because the project environments are self-contained and Julia does not like to pick things from outside. That makes your environment is very reliable, that they will work, they will not have missing things. But it also implies that Julia installs a lot of stuff that actually is already available in the system. Like for instance, here, this environment that I just created will have OpenSSL. With OpenSSL is always available in your system. It will have FFTW, that's the fast Fourier transfers, which we have as modules as well. And a bunch of stuff that like Qt6, FFmpeg, libdiff, all of that stuff those are libraries that are not Julia libraries. Those are probably code in C or C++. They are standard libraries. But as I said, Julia wants to self-contain everything so that it's reliable. So it will install everything inside this environment. And then it will do all kinds of compilations and things. And it will end up, for instance, here installing 76 packages. But that's it. So once this is done, your environment will have the tight binding toolkit installed, and you can use it just by using tight binding toolkit, and then you are good for the races. However, it's also important, as I said, the projects in Julia can become very big because, as you have seen, it installs everything that it needs at all levels. So as a recommendation, we recommend to move your .julia directory that exists in your home directory into the VSC Scratch and just create a symlink between the one in your home directory to the one in your VSC Scratch. And that will just avoid that you fill in your home quota with Julia projects. And that's it. Now the environment is installed and I can actually just use it. And that should work. Voila. And now, just as a last remark, there's actually a way to actually combine our projects with modules. It's a bit complicated, so I'm just drop it here. If you're interested, look at this slide. Basically, what you can do is take the module that has the Julia package that you want to use as base. In this case, it's called Circuitscape. And then you can just copy the environment of that module into your own one, which it's creating a new folder, but instead of being an empty folder, is a folder for a project that already has the definitions of the environment in the module. And then you can just start using it. So you activate it as usual, and then you will see that, for instance, my new environment here has Circuitscape already available, and we have not installed anything. And then on top of this, you can install your own stuff. But well, this is a bit advanced. And I left some homework for those interested in R and Julia, if you want to try it out. Just to actually, in R, how would you define a specific version of BGDB to be installed? Because, for instance, VUB Manager just picked 232 because that's the one that works with our modules, which is very nice. But if you needed a different one, what could you do? Also, you can try to install Ninjater from the GitHub repository instead of the repositories in Bioconductor or CRAN. And the same for plots.jl. You can try to add a package to the tight binding toolkit. And that's it. If you have any questions.
I stand corrected. We're perfectly on time. Any questions on R and Julia? One in the chat.
There's one there.
Okay, let me do the one in the chat first, maybe. When I tried using RStudio via the on-demand app with RLibs on VSC data, RStudio kept crashing. Is the R project way the only way to work in RStudio and RLibs on VSC data? Could you explain how RStudio relates to R on the HPC? That's 3 questions in one, I guess, but...
Yes, so, well, manipulating RLibs is not really a good way to do that change. If you want to manipulate, if instead of using R projects, you want to manipulate the libs, you should use the RLibs home. That allows you to set a custom path for your user library in R. It still has all the problems of using your user library in R, like it's tied to a single version of R. It's not, you cannot activate, deactivate packages like you can do with R projects, but at least it will not be in your home directory. If you want to change the R libs, like the system-wide, that I'm not surprised that breaks things. Yeah, you're not supposed to do that.
But I guess the VSC wrapper tool should give a better experience when combining it with RStudio, right? So that's definitely, I mean,
or using projects in RStudio. I mean, that's the recommended way.
Yeah, that was actually one of the motivators, I think, for the VSC our project tool. Yeah, all right. Seems like that question was answered. So yeah, there was another question here in the room.
Yes, hello. You mentioned that if you install R packages via the VSC environment, that it's possible to share it with other colleagues. But how would you share software that is installed in your VSC data with your colleagues then?
But you can just copy the folder.
Just copy.
Yeah.
But then if I install something, they have to copy it again.
Yeah, exactly. Or, well, but if you have, are you from, depending on your site, so if you're from Ghent or Brussels and you are in a virtual organization, you can easily have a shared folder in there. And you can just put this project in a shared folder that everybody has access to. Or if you are in Leuven, I guess that you might have a project folder where everybody has access to. You can just put these projects in there and that works.
Okay, thanks.